The oldest picture ever taken shows a newborn universe. This image is not made of pixels, but of ancient light, a cosmic fossil from a time before stars or galaxies even existed. By the end of this journey, you will understand how scientists read this light to reconstruct the entire lost history of the cosmos, from its fiery first moments to the silent era before dawn. How did everything we see emerge from near-perfect nothingness, and what invisible forces are still stretching the fabric of reality? What does it mean for us, living in this fleeting moment of cosmic time, to have decoded the story of our own origins? That ancient snapshot is possible because light is the universe's ultimate messenger. It travels across the cosmos not as a silent beam, but as a detailed report, carrying the story of everything it has touched. To read the history of the cosmos, we first need to understand the language of light itself. Its most profound property is its speed, which is not infinite but fixed, a universal speed limit. This simple fact changes everything. When you look at the moon, you see it not as it is now, but as it was about 1 second ago, because that is how long its light took to reach your eyes. When you look at the sun, you see it as it was 8 minutes in the past, and when our most powerful telescopes peer at a distant galaxy, they are not seeing its present state. They are receiving a signal that has been traveling for millions or even billions of years. Every telescope is, in its essence, a time machine. This principle, called look-back time, means the deeper we gaze into space, the further back we journey into cosmic history. But light is more than just a signal with a time stamp. It is a full spectrum of information. What our eyes perceive as visible light, the colors of the rainbow, is just a tiny slice of a vast electromagnetic spectrum. This spectrum includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Different cosmic events and objects broadcast their stories on different wavelengths. A cold cloud of gas in deep space whispers in radio waves. A blazing young star screams in ultraviolet. By learning to listen across this entire spectrum, astronomers can piece together a complete picture of the universe's conditions across time. The real magic, however, is in the details embedded within that light. When light passes through or is emitted by matter, it leaves unique fingerprints. Imagine you are a detective analyzing a piece of cloth found at a scene. Under a special light, you might see stains or fibers that reveal where the cloth has been and what it contacted. Light works the same way. As it journeys from a distant star or galaxy, it passes through clouds of gas. Atoms in those gases absorb very specific wavelengths of light, leaving dark lines in the spectrum like barcodes. These are called absorption lines. Conversely, hot, energized gases emit light at specific wavelengths, creating bright emission lines. By reading these lines, astrophysicists can decode the exact chemical composition of a distant object, measure its temperature, and even determine how fast it is moving toward us or away from us. This is how we know the sun is made of hydrogen and helium, and how we discovered the universe is expanding. This foundational understanding transforms our view of the night sky. We are not just looking at points of light, we are reading billions of individual cosmic diaries, each page written in the unique language of photons. With this key in hand, we are finally ready to seek out the oldest diary of all, the one written when the universe was just an infant, a relic of light that has been traveling to us since before the first star was born. That ancient burst of light did not simply vanish into the void. It is still here, all around you, right now. It fills every cubic inch of the room you are in. It passes through the walls of your home, and it even echoes through the vast emptiness between galaxies. This is the cosmic microwave background radiation, the oldest light in the universe. It is the direct, cooled remnant of the moment the cosmos itself became transparent. To understand what that means, we have to step back to a time before time, as we know it, had even begun. In its earliest moments, the universe was an unimaginably hot, dense soup of fundamental particles and searing radiation. Light particles, called photons, could not travel any meaningful distance. They were constantly bouncing off a thick fog of free electrons, like someone trying to walk through a crowded, chaotic room where everyone is constantly bumping into them. The universe was opaque, a brilliant, blinding fog. Then, about 380,000 years after the Big Bang, everything changed. The expanding cosmos had cooled enough for electrons to finally combine with protons, forming the first stable atoms, mostly hydrogen. This pivotal event is called recombination. Suddenly, the fog cleared. With most electrons now bound inside atoms, the photons had a clear path. That primordial light, which had been trapped since the beginning, was finally set free. That first flash of liberated light is what we detect today as the cosmic microwave background. It is not coming from one direction in the sky. It is coming from everywhere at once. It is the afterglow of creation itself. The discovery of this cosmic echo is a story of brilliant accident. In the mid-1960s, two radio astronomers named Arno Penzias and Robert Wilson were working with a large, sensitive horn antenna in New Jersey. They were plagued by a persistent, faint hiss of microwave noise that came from every direction and would not go away. They meticulously cleaned out pigeon nests and electronics, but the noise remained. It was not a malfunction, it was the universe whispering to them. They had stumbled upon the cooled remnant of the Big Bang's first light, a discovery that would earn them the Nobel Prize and forever change our understanding of cosmic origins. Today, that light has been stretched and cooled by the relentless expansion of space over 13.8 billion years. The once searing, visible light has been redshifted all the way down into the microwave part of the spectrum. Its temperature is a mere 2.7 degrees above absolute zero, the coldest possible temperature. This makes the entire universe, even its emptiest voids, just slightly warmer than the deepest cold imaginable. What makes this glow so profoundly informative is its near-perfect character. Its spectrum is what physicists call a blackbody curve, the signature of an object in perfect thermal equilibrium. It is the most perfect blackbody ever measured in nature, a pristine relic of a time when the universe was smooth, hot, and simple. Yet for all its perfection, it is not perfectly uniform. If it were, our universe would be a featureless, eternal sea of hydrogen gas. There would be no stars, no galaxies, no planets, and no us. The true magic, the secret of our existence, is written in the faintest of imperfections. Embedded within that uniform microwave bath are tiny variations in temperature, minuscule ripples that represent the seeds of all cosmic structure. These are the quantum fingerprints from the universe's first moments, stretched to cosmic scales, and they hold the blueprint for everything that would ever form. To read our cosmic fate, we must learn to see those whispers in the afterglow. The entire cosmos was painted onto a canvas of nearly perfect uniformity. But perfection in the universe is a recipe for eternal stillness. To find the origin of motion, of structure, of life itself, we must search for the flaws in that perfection. The story of everything is written in deviations so slight they defy belief. The temperature of the cosmic afterglow is not exactly the same in every direction. If you could feel it with your hands, the difference between a slightly warmer patch and a slightly cooler one would be about 1 part in 100,000. To put that in perspective, if the background radiation were an ocean, these variations would be ripples no taller than a sheet of paper. Yet these microscopic brushstrokes on the cosmic canvas are the most important map we have ever found. Scientists call these tiny fluctuations anisotropies, meaning the property is not the same in all directions. They are not random static. They form a specific, intricate pattern across the entire sky, a pattern that has been meticulously mapped. This incredible cartography was the work of generations of satellites, each more sensitive than the last. The Cosmic Background Explorer, or COBE, first saw the rough outline of these ripples in the early 1990s, proving they were real. The Wilkinson Microwave Anisotropy Probe, WMAP, refined the image into a detailed portrait. Finally, the Planck satellite delivered a map of breathtaking precision, a full sky snapshot of the infant universe in exquisite detail. But what are we actually seeing in this speckled map of the sky? Each tiny hotspot, each faint cold spot, is a fossilized imprint of a quantum event from the universe's first fleeting moments. In that inconceivably early time, space itself was a seething quantum foam. Tiny fluctuations in energy, mere ghosts of particles flickering in and out of existence, were caught in a cosmic trap. In a fraction of a second, a period called inflation, the universe expanded faster than the speed of light, stretching those quantum whispers to sizes larger than galaxies. What was once a subatomic hiccup became a continent-scale variation in density. The slightly denser patches, shown as warmer spots in the microwave background, held a tiny bit more gravitational pull. The cooler spots were the slightly emptier valleys. This pattern, frozen into the fabric of spacetime when the universe became transparent, became the ultimate blueprint. It dictated where gravity would begin its slow, relentless work of assembly over billions of years. Every galaxy cluster, every filament of the cosmic web, every vast empty void can trace its lineage back to a specific set of ripples on this map. By reading the statistical properties of these anisotropies, their size and distribution, cosmologists can answer profound questions. They can measure the geometry of the universe itself, determining if space is flat, curved, or closed. They can inventory the cosmos, calculating the precise amounts of ordinary matter, and dark energy. This map is the universe's birth certificate and its architectural plan rolled into one. It tells us not only how the cosmos began, but what it was destined to become. With this blueprint in hand, the next chapter of the story asks a monumental question. How did a nearly smooth universe, marked only by these paper-thin ripples, transform into the spectacularly clumpy and structured cosmos we inhabit today? The answer lies in a silent, patient force that worked in the darkness for eons before the first star ever shone. The faint ripples in the cosmic afterglow are not the only whispers from creation. There is a deeper, more elusive signal hidden within that ancient light, a ghostly imprint from an event so violent it stretched the very fabric of reality. To find it, we must look not just at the temperature of the light, but at its orientation, a property called polarization. As the cosmic microwave background radiation washes over us, its light waves vibrate in specific directions, like sunlight glinting off the surface of a lake. This polarization comes in two distinct types, which scientists call E-mode and B-mode. The E-mode pattern is relatively straightforward, a radial or curl-free arrangement caused by the simple scattering of light-off electrons in the primordial plasma. It is the expected signature of the hot and cold spots we have already mapped. The B-mode pattern, however, is something else entirely. It represents a twisting, a curl in the polarization map, like the pattern left in water after stirring it with a spoon. This twisting signature is the potential smoking gun for one of cosmology's most profound ideas, cosmic inflation. The theory of inflation proposes that in the first unimaginably tiny fraction of a second after the Big Bang, the universe underwent a growth spurt of staggering violence. It expanded exponentially faster than the speed of light, doubling in size perhaps 100 times or more in less than a blink. This explosive event would have done more than just stretch quantum fluctuations into cosmic seeds. It would have shaken the foundations of spacetime itself, generating powerful ripples known as primordial gravitational waves. These are not waves in water or air, but literal distortions in the geometry of the cosmos, stretches and squeezes in the fabric of reality as it expanded. If these gravitational waves existed, they would have left their unique, twisting signature on the polarization of the cosmic microwave background, creating those telltale B-modes. Finding this signal is the holy grail for many cosmologists. As one leading researcher put it, detecting primordial B-modes would be like opening a window to the universe at 1/1,000,000,000th of a second old. It would provide direct evidence for physics at energy scales 1,000,000,000,000 times higher than anything our most powerful particle colliders can ever hope to reach. The hunt for this ghostly imprint is at the very frontier of experimental cosmology. Projects like the BICEP and Keck array telescopes at the South Pole stare at the cleanest, driest patches of sky, searching for this faint curl in the polarization of the ancient light. The quest is immensely difficult as the signal is incredibly faint and can be mimicked by foreground interference like dust within our own galaxy. While a definitive, uncontested detection remains elusive, the search itself connects the very largest scales of the cosmos to the very smallest rules of particle physics. It bridges the story of the universe's explosive birth to the fundamental particles that would eventually become its building blocks. If those primordial gravitational waves are real, they tell us that the universe did not just begin with a bang, but with a resonant, space-shaking shudder, a vibration that still echoes silently through the expanding darkness. The universe's first moments were not silent. They were filled with a deafening roar. In that searing plasma of the early cosmos, sound waves of immense power raced outward, sculpting the distribution of matter on a scale so vast it would take billions of years for us to see the pattern. These are the Baryon acoustic oscillations, and they are perhaps the most elegant cosmic fossils we have ever discovered. To understand them, think of the infant universe not as a static soup, but as a dynamic, churning fluid. Within that fluid, ordinary matter, which scientists call baryons, and light, made of photons, were locked in a fierce tug of war. They were coupled together, a single entity where photons exerted immense outward pressure, while the gravity of the baryons pulled inward. This created a cosmic oscillator. Any slight overdensity, one of those quantum seeds from inflation, would act like a stone dropped into a pond. A spherical pressure wave, a sound wave of incredible energy, would rush outward through the plasma. But this was not sound as we know it. The medium was so hot and dense that these waves traveled at over half the speed of light, a supersonic boom on a universal scale. This frantic dance continued for nearly 400,000 years, with wave after wave expanding from every single seed across the cosmos. Then, at the moment of recombination, everything changed. When the universe cooled enough for atoms to form, the photons suddenly decoupled. They streamed away, becoming the cosmic microwave background we see today. With the photon pressure gone, the outward rush of the baryonic matter waves stopped instantly, frozen in place. Picture a circular ripple in a pond suddenly turning to solid ice, capturing the wave at its maximum extent. That is what happened across the entire cosmos. These frozen waves left a distinct, predictable signature in two places. First, they are imprinted subtly in the pattern of hot and cold spots in the microwave background itself. Second, and more profoundly for mapping the later universe, they created a spherical shell of slightly higher matter density at a very specific distance from the center of each original seed. Over billions of years, as gravity pulled matter into galaxies and clusters, it preferentially formed at these enhanced density shells. The result is that if you could map the positions of millions of galaxies across the sky, you would find a subtle statistical preference for galaxies to be separated by a certain distance. That distance is the radius of that frozen sound wave, a cosmic standard ruler etched into the fabric of space. This ruler is astonishingly valuable because its true physical size is known from the physics of the early universe, calculated from the conditions we see in the cosmic microwave background. By observing how this ruler appears to us at different distances, and therefore different times in cosmic history, astronomers can measure the expansion rate of the universe with remarkable precision. It is like finding a yardstick of known length embedded in the cosmos at various depths. By seeing how stretched or compressed that yardstick appears, we can chart exactly how space itself has stretched over time. This gives us an independent, powerful cross-check on our cosmic history, connecting the blueprint of the early universe directly to the grand structure we see today. It confirms that the story written in the ancient light is the same story told by the galaxies themselves. With this confirmation in hand, we have a robust timeline, a map of expansion. But this map reveals a profound and unsettling mystery, a discovery that suggests most of the universe is made of something we cannot see and do not yet understand. The entire universe was once a brilliant, impenetrable fog. For nearly 400,000 years after its explosive beginning, our cosmos was not a place you could see through because light itself was trapped. It was a searing plasma, a churning sea of fundamental particles where protons and electrons roamed free, unbound and electrically charged. In this chaotic environment, photons, the particles of light, had no peace. The moment one began to travel, it would immediately collide with a free electron, scattering in a new direction. It was like trying to walk in a blizzard where every snowflake deflects your path, a constant, blinding scatter that made the universe completely opaque. Light could not travel in straight lines, so no signal, no image, no story could be carried across space. The cosmos was a self-contained prison of brilliance. Then a pivotal threshold was crossed. As the universe relentlessly expanded, it also cooled. The average energy of particles dropped below a critical point. Suddenly, the roaming electrons could be captured. They were grabbed by protons, combining to form the first stable atoms, almost entirely hydrogen. This monumental event is known as recombination. In a cosmic sense, it was the moment the fog lifted. With the electrons now bound inside neutral atoms, the traffic cleared. The photons, which had been bouncing around for eons, suddenly found open road. They were no longer scattered, they were set free. This sudden decoupling of light from matter is the single most important event for cosmic historians. The instant those photons began streaming freely, they carried with them a perfect snapshot of the universe as it was at that exact moment. They have been traveling in straight lines ever since for over 13 billion years. The sphere from which they originate is called the surface of last scattering. It is not a physical shell out in space, but a moment frozen in time, a cosmic horizon that exists at a specific distance in every direction we look. Every point in our sky corresponds to a point on that ancient surface. When we detect the cosmic microwave background, we are effectively looking at a panoramic photograph of the universe on its 380,000th birthday. The properties of this light are not random. They are a direct probe, a forensic record of the conditions during recombination. The light's near-perfect blackbody spectrum tells us the universe was in a state of exquisite thermal equilibrium, with a temperature of about 3,000 degrees Kelvin. Its incredible uniformity reveals a cosmos that was smooth to 1 part in 100,000, a testament to its violent inflationary birth. And those tiny, vital fluctuations in temperature are the imprints of the quantum seeds that would later become galaxies. This transparency event was the universe's first true dawn. Before it, history was a local, hidden affair, written in a plasma too hot to read. After it, history became a story carried on beams of light, a narrative that could travel across the ages. The universe had finally opened its eyes, and the first thing it saw was its own glowing, simple face, a portrait of potential from which everything we know would slowly, gravitationally emerge. The universe had finally become transparent, but in a profound sense it went dark, with the last echoes of the primordial glow now streaming freely into the expanding void. A profound silence descended. For the next several 100 million years, the cosmos entered a chapter known as the Cosmic Dark Ages, an era devoid of any new light. No stars burned. No galaxies swirled. The brilliant, searing plasma of the infant universe had cooled into a vast, featureless sea of neutral hydrogen and helium gas, drifting in the deepening cold and darkness. The only illumination was the fading afterglow of the Big Bang itself, stretching further into the microwave spectrum with each passing eon, its light too feeble to see and carrying no news of current events. It was a universe between acts, holding its breath. This period is the great missing chapter in our cosmic history book. We have the brilliant opening scene, the flash of recombination, and we have the spectacular later chapters filled with galaxies. But the pages in between, detailing how a smooth, dark gas cloud became a structured, luminous cosmos, are frustratingly blank to our telescopes. We cannot see this era directly because there was nothing to see, no new sources of light to send us a signal. To study the Dark Ages, astronomers must become cosmic detectives, looking for the shadows this era cast upon the light that came after. The key lies in that sea of neutral hydrogen gas. This primordial gas does not emit visible light, but it does interact with specific, very precise wavelengths of light that pass through it. When the first luminous objects finally ignited, their brilliant light began to stream through the cosmic fog. The hydrogen atoms acted like a filter, absorbing a very particular shade of ultraviolet light. This absorption leaves a distinct, dark fingerprint in the spectrum of any ancient object shining from behind the fog. It is like finding a stained glass window and, by studying the exact colors of light that are missing, deducing the composition of the glass itself. By analyzing the spectra of the most distant quasars, brilliant beacons powered by supermassive black holes, astronomers have detected this universal shadow. They can see how the absorption grows stronger the further back they look, mapping the extent and density of the neutral hydrogen fog that once filled all of space. The cosmic dark ages were not a period of stagnation, however. They were a period of immense potential, a quiet incubation. Within that uniform darkness, the gravitational seeds imprinted in the cosmic microwave background were at work. The slightly denser patches of gas, those fossilized quantum ripples, very slowly began to pull in more material from their surroundings under their own gravity. The universe was not yet clumpy with stars, but it was beginning to gather itself, drawing invisible lines of force that would become the skeleton of the cosmic web. This silent, gravitational knitting was the essential preparation for the drama to come. The length of the Dark Ages, hundreds of millions of years, was set by a simple cosmic race. How long would it take for gravity to overcome the expansion of space and the internal pressure of the gas to finally collapse a cloud and ignite the first nuclear furnace? The answer would rewrite the history of the cosmos, ending the long night with a sudden, transformative dawn. That profound cosmic silence could not last forever. Deep within the densest knots of the invisible gas clouds, a slow, relentless force was at work. Gravity, the patient architect of the cosmos, was finally overcoming the expansion of space and the outward pressure of the gas itself. In the hearts of those primordial clouds, composed almost entirely of hydrogen and helium, the pressure and temperature began to rise, climbing to unimaginable levels. When the core temperature reached about 10 million degrees, a new and fundamental fire ignited. The nuclei of hydrogen atoms, under that immense pressure, began to slam together in a process called nuclear fusion, forging helium and releasing a torrent of energy. The first star was born. Its light pierced the universal darkness, ending the long cosmic night. These first stars, known to astronomers as population 3 stars, were unlike anything in our modern galaxy. Formed from the pristine, unpolluted gases of the early universe, they were likely behemoths, hundreds of times more massive than our Sun. They burned with a ferocious, blue-white intensity, and their lives were spectacularly brief, perhaps lasting only a few million years before exploding in cataclysmic supernova. These titans did not just illuminate the darkness, they fundamentally changed the chemistry and structure of the cosmos. In their violent deaths, they forged and scattered the first heavy elements, like carbon and oxygen, seeding the universe with the raw materials for future stars, planets, and life itself. But the light from these first stars did something else, something that transformed the very nature of space. Their intense ultraviolet radiation began to blast through the surrounding fog of neutral hydrogen. This high-energy light carried enough punch to knock electrons loose from their atoms, a process called reionization. Imagine a dense morning fog slowly burning away under a rising sun. That is what happened on a cosmic scale over hundreds of millions of years. The ultraviolet starlight from these first galaxies and stars gradually reionized the hydrogen gas that filled the space between them, stripping the electrons that had been bound since the era of recombination. This pivotal transition, known as the Epoch of Reionization, made the universe transparent once more to ultraviolet light, clearing the intergalactic medium and setting the stage for the light from all future stars and galaxies to travel freely. We cannot see these first stars directly. Their light is far too faint and has been stretched into the infrared by the expansion of the universe. Instead, astronomers detect the shadow of this epoch. They use the most brilliant beacons in the distant cosmos, quasars, as cosmic flashlights. By analyzing the spectrum of light from a quasar that has traveled billions of years to reach us, scientists can see a specific pattern of absorption lines. These dark lines are the fingerprints of neutral hydrogen gas the light passed through on its journey. As they look at quasars at different distances and therefore different times, they observe a clear trend. The farther back they look, the stronger the neutral hydrogen absorption becomes. This tells a story of a universe gradually transitioning from a neutral fog to an ionized clearness. The Epoch of Reionization was not an instant flip of a switch, but a gradual, patchy process, as bubbles of ionized gas grew around clusters of early stars and galaxies, eventually overlapping to fill the cosmos. This dawn was the universe's second great awakening. The first was the flash of light at recombination, when the cosmos became transparent to its own afterglow. The second was this era when starlight itself began to sculpt and clear the cosmic medium. The light from those first monstrous stars, though we may never capture it directly, carries the indelible signature of the universe's first major transformation since its birth, the moment it moved from a simple, dark sea of gas to a complex, structured, and luminous home for everything to come. The end of the cosmic dark ages was heralded by titanic beacons, piercing the gloom from the very edge of observable time. These are quasars, the brilliant hearts of the universe's first galaxies, shining with the light of 1 trillion suns from a time when the cosmos was just a fraction of its current age. Their power source is one of the most extreme phenomena in nature, a supermassive black hole, millions to billions of times the mass of our own sun, caught in a frenzy of consumption. As vast clouds of gas and dust spiral into the black hole's gravitational grip, they form a searing, glowing disk of material called an accretion disk. The friction and magnetic forces within this disk heat it to millions of degrees, causing it to blaze across the entire electromagnetic spectrum before the matter vanishes forever behind the event horizon. This process is so ferociously efficient at turning mass into light that a single quasar can outshine every star in its host galaxy combined, making them visible to our telescopes across more than 13 billion light-years of expanding space. This incredible luminosity is what makes quasars such powerful tools for cosmic historians. They act as the ultimate lighthouses, their brilliant beams shining through the vast, silent expanses between galaxies. As that light journeys toward us for billions of years, it does not travel through a perfect vacuum. It passes through the diffuse intergalactic medium, a faint fog of mostly hydrogen gas that was left over from the Big Bang and later enriched by the explosions of early stars. This gas leaves its mark on the quasar's light in a breathtakingly detailed way. When astronomers spread the quasar's light into a spectrum, breaking it into its constituent colors like a rainbow, they do not see a smooth band. Instead, they see a dense, intricate pattern of dark lines slicing across it. This is known as the Lyman-Alpha Forest, and each one of those thousands of lines is a story waiting to be read. Each dark line is an absorption line caused by a specific cloud of hydrogen gas at a precise distance along the line of sight. The light from the quasar, as it passes through a cloud, has a very specific shade of ultraviolet light absorbed by the hydrogen atoms within it. Because the universe is expanding, light from more distant clouds is stretched or redshifted more than light from closer clouds. This means each absorption line is shifted toward the red end of the spectrum by an amount that tells us exactly how far away its cloud is. The result is a cosmic barcode. The dense thicket of lines near the quasar's own redshift represents clouds close to it in the early universe. As we look at lines shifted less and less, we are seeing clouds that are progressively closer to us in both space and time. By decoding this barcode, scientists can create a three-dimensional map of the hydrogen gas distribution across cosmic history. They can see how the gas, which began nearly smooth, clumped into filaments and voids under gravity, weaving the cosmic web. They can measure when the gas transitioned from neutral to ionized during the Epoch of Reionization, because ionized hydrogen leaves a different signature than neutral hydrogen. The changing density of the forest over time is a direct record of the universe's structural growth and chemical enrichment during its most formative years. Quasars thus provide a vital, complementary narrative to the one told by the cosmic microwave background. The CMB gives us a pristine baby picture, a single snapshot of the universe at 380,000 years old. Quasar spectra offer us a continuous documentary, a journey through time from that early infancy into the chaotic adolescence of galaxy formation. They illuminate the messy, complex processes that happened after the universe became transparent, showing us how the pristine conditions revealed by the afterglow were gradually sculpted into the rich and structured cosmos we see today. By studying these cosmic lighthouses, we are not just looking at brilliant points of light. We are using their beams to illuminate the shadowy scaffolding of the universe itself, tracing the invisible architecture upon which galaxies would eventually be built. A galaxy is not a single object but a vast community of stars, each with its own story. When we point our telescopes at a distant galaxy, we are not collecting the light of one star, but the combined glow of billions, a chorus of histories blended into a single beam. This integrated light is the galaxy's complete spectral fingerprint, a composite archive that chronicles its entire life, from its first fiery generation of stars to its most recent newborns. By learning to read this complex signature, astronomers can reconstruct a galaxy's biography in astonishing detail. The first clue lies in the overall color of the galaxy's light. A galaxy glowing with a reddish hue is generally an older, more settled system, dominated by long-lived, cooler stars. A galaxy shining with a fierce blue light is a stellar nursery, alive with the intense radiation of massive, hot, and short-lived stars. But the true story is told in the fine lines etched across its spectrum. Deep, dark absorption lines like those from calcium or iron are the hallmarks of older stellar populations. These are the fingerprints of countless sun-like stars, whose cooler atmospheres absorb specific colors of the light welling up from their cores. In contrast, bright emission lines glowing in hydrogen alpha or oxygen signal the presence of searing hot gas. These are the beacons of active star formation, where ultraviolet radiation from newborn stars excites the surrounding nebulae, causing them to fluoresce like a cosmic neon sign. By measuring the strength of these features, scientists can calculate the galaxy's star formation rate, estimate the average age of its stellar population, and even determine its chemical composition, tracing how enriched it has become with elements forged in successive generations of stellar explosions. Yet perhaps the most profound information carried in a galaxy's light is not about its nature but its motion. As the light journeys across an expanding universe, its wavelengths are stretched, shifting the entire spectrum toward the red end. This cosmological redshift is a direct measure of both how fast the galaxy is receding from us, and because light takes time to travel, how far back in time we are looking. A galaxy with a small redshift is relatively nearby and shows us its recent state. A galaxy with a tremendous redshift is an ancient relic, its light revealing its appearance when the universe was young. This gives astronomers a powerful tool, a way to rewind the cosmic film. By observing thousands of galaxies at different redshifts, we can arrange them not by distance but by age. We can watch the narrative of galactic evolution unfold. The earliest galaxies seen at the highest redshifts are often small, irregular, and chaotic, blazing with furious star formation as they pull in gas and frequently collide with their neighbors. These are the building blocks of the majestic structures we see today. Over billions of years, through a stately dance of mergers and acquisitions, these chaotic clumps coalesce. Major mergers can trigger intense bursts of star formation before settling into smooth, featureless elliptical galaxies. More peaceful accretion of gas allows an ordered spiral disk to form and persist, with star formation continuing in its graceful arms. The light from each galaxy is a living archive, a cumulative record of all these events, its spectrum a palimpsest written over by every generation of stars. This grand story of assembly, from tiny seeds to grand designs, was all pre-written in the faintest of beginnings. The subtle density variations frozen into the cosmic microwave background provided the gravitational blueprint, the starting points where dark matter first began to gather. The light from galaxies shows us the breathtaking result, how simple whispers in the afterglow were patiently translated over cosmic time into the complex and luminous civilizations of stars we now call home. The grand story of galactic light is a chronicle of birth and assembly, but it is also a record of spectacular death. A single star, in its final moments, can unleash a flash of energy so brilliant it temporarily outshines every other star in its galaxy combined. This is a supernova, the catastrophic end for a massive star, and its light does far more than signal an ending. It serves as both a precise cosmic measuring stick and the universe's most powerful chemical forge. When a star many times more massive than our Sun exhausts its nuclear fuel, its core can no longer support its own immense weight. In a fraction of a second, it collapses, triggering a shockwave that blasts the star's outer layers into space at nearly a tenth the speed of light. This core collapse supernova is a titanic event, but it is not the only kind. Another type, known as a Type 1, a supernova, occurs in a binary star system where a dense white dwarf star steals material from its companion. When the dwarf reaches a critical mass, it undergoes a runaway thermonuclear explosion, completely destroying itself. These two paths to destruction have distinct signatures in their light, and both are indispensable to cosmic history. The light from a Type 1, a supernova, is particularly special because its brightness follows a very predictable pattern. Since these explosions always happen at roughly the same critical mass, they reach nearly the same peak luminosity. This makes them what astronomers call standard candles. If you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its distance with remarkable accuracy. In the late 1990s, teams of astronomers used distant Type 1, a supernova, as mileposts to measure the expansion rate of the universe across billions of years. They made a startling discovery. The universe is not just expanding, its expansion is accelerating. Something is pushing galaxies apart faster and faster over time. That mysterious something was named dark energy, and its discovery, guided by the light of dying stars, revolutionized our understanding of cosmic fate. But a supernova's light carries another, equally vital story, written in the colors it emits. In the unimaginable heat and pressure of the explosion itself, atomic nuclei are smashed together in a process called explosive nucleosynthesis, forging elements far heavier than those made during the star's stable life. A core collapse supernova scatters the elements forged in its progenitor star's core, like oxygen, neon, and silicon, and creates even heavier ones like gold and uranium in the blast itself. The light from the expanding supernova remnant passes through this newly created cloud of debris. As it does, the specific elements present absorb and emit light at their own unique wavelengths, imprinting a direct chemical fingerprint onto the spectrum of the explosion. By reading this spectral signature, astronomers can literally see the freshly forged iron, cobalt, nickel, and silicon being flung into the void. This is how we know that nearly every atom in our bodies heavier than hydrogen and helium was once forged in the heart of a star and scattered by a supernova explosion. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created in these stellar cataclysms. Each supernova enriches the surrounding interstellar gas with these heavy elements, or metals as astronomers call them. Over generations, this chemically richer gas collapses to form new stars and planets. Stars born from this enriched material, like our own Sun, are already seeded with the ingredients for rocky worlds. The light from supernova, therefore, connects the life cycle of stars directly to the possibility of planets and life. It tells a continuous story of cosmic chemistry, where the violent death of one generation provides the essential materials for the birth of the next. In this way, the flash of a supernova is not just a brilliant endpoint, it is a luminous seed, planting the elements of future complexity across the darkness of space. The universe's most brilliant forges and most precise mileposts all rely on light that is emitted. But what about the light that is bent? A century ago, Albert Einstein's theory of general relativity made a startling prediction. Massive objects do not simply exert a pull, they warp the very fabric of space-time around them. And since light travels along the contours of this fabric, its path is not always straight. A massive object, like a galaxy or a cluster of galaxies, can act as a cosmic lens, bending and distorting the light from objects far behind it. This phenomenon, called gravitational lensing, turns the cosmos into a hall of mirrors and magnifying glasses, allowing us to see the invisible. When the alignment is nearly perfect, the effect is spectacular and unmistakable. This is strong gravitational lensing. The immense gravity of a foreground galaxy cluster can warp the light from a single background galaxy into multiple images, smearing it into bright arcs or even a complete circle of light known as an Einstein ring. These celestial mirages are not just beautiful curiosities, they are powerful tools. By studying the distortion, astronomers can map the distribution of all the mass in the foreground cluster, including the vast halos of dark matter that betray their presence only through gravity. The lens acts as a natural telescope, magnifying the faint, distant galaxy, bringing into view details of its structure that would otherwise be lost to the immense distance. But lensing is not always so dramatic. More common is weak gravitational lensing, where the alignment is less perfect. Here, the shapes of thousands of background galaxies are subtly stretched and sheared by the gravitational field of the intervening matter. No single galaxy shows a clear distortion, but by analyzing the statistical alignment of countless galaxy shapes, scientists can create a mass map of the cosmic web itself, tracing the vast filaments of dark matter that connect clusters across the void. This is how we see the invisible skeleton of the universe. On the smallest scale, there is microlensing. This occurs when a compact object like a star, a planet, or even a black hole passes directly in front of a more distant star. The foreground object's gravity briefly focuses the background star's light, causing a temporary characteristic brightening. Microlensing is a powerful method for detecting objects that emit no light of their own, from rogue planets wandering between stars to stellar mass black holes, by the fleeting shadows they cast upon the light of others. The profound power of gravitational lensing is that it reveals matter purely through its gravitational influence. It does not require the matter to glow to emit any radiation at all. It shows us the dark universe directly by how it bends the light from the luminous universe. This connects the story all the way back to the beginning. Those tiny ripples in the cosmic microwave background, the anisotropies, were the seeds for the uneven distribution of all matter, both light and dark. Gravitational lensing allows us to trace how those seeds grew into the massive clusters and filaments that now sculpt the paths of light across the cosmos. The light we see is not just a message, it is a probe, its very path a testimony to the hidden architecture it has traveled through. And this architecture, we now understand, is dominated by a mysterious component that not only bends light but governs the ultimate fate of the cosmos itself. Every flash of starlight, every quasar's blaze, and every supernova's final burst has contributed to a permanent addition to the cosmos. Beyond the light we see from individual galaxies lies a faint, omnipresent glow, the integrated sum of every photon that has ever escaped a celestial source and still travels freely through space. This is the extragalactic background light, the universe's total luminous fossil. It is not a light you can see with your eyes or even a traditional telescope, for it is an incredibly dim bath of radiation that has been stretched and diluted by the expansion of the universe over billions of years, spanning from the ultraviolet through the optical and into the far infrared. This glow represents the ultimate census of cosmic energy production, a cumulative record of every star that has ever shined and every black hole that has ever feasted across all of time. Because this background is so incredibly faint and diffuse, astronomers cannot point an instrument at an empty patch of sky and measure it directly. Instead, they detect it by observing its shadow. They use the most energetic photons in the universe as probes, gamma rays from distant blazars, which are galaxies with jets of particles pointed almost directly at Earth. As these brilliant, high-energy gamma rays travel across the cosmos toward us, they have a chance of colliding with the much lower energy photons of the extragalactic background light. When a high-energy gamma-ray photon meets a background light photon, they can annihilate each other, creating matter. This process means the gamma rays from the most distant blazars should be gradually attenuated or dimmed on their long journey to Earth. By carefully measuring the spectra of these distant gamma-ray sources and comparing them to closer ones, scientists can deduce the density and the spectrum of the invisible sea of background light that caused the absorption. It is a remarkable method, using the brightest, most violent beacons to illuminate the faintest, most universal glow. What this global glow tells us is a story of cosmic productivity. The spectrum of the extragalactic background light is a timeline of star formation and energetic activity. The ultraviolet and optical parts of this background were predominantly produced during the universe's more active youth, when galaxies were forming stars at a furious rate. The infrared portion largely comes from that starlight absorbed by cosmic dust within galaxies, and re-radiated at longer, warmer wavelengths. By analyzing the intensity of this glow across different wavelengths, cosmologists can test their models of how galaxies assembled and evolved over time. They can ask, does the total light produced over 13.8 billion years match what we predict from counting galaxies at different epochs? The answer provides a crucial check, ensuring our snapshot view of cosmic history adds up to a consistent whole. This pervasive, whisper-thin light is the universe's background hum, the static left over from all its luminous conversations. It is the collective echo of existence, a reminder that every point of light we see in the night sky is part of a grand, integrated narrative. While telescopes show us specific chapters, like the brilliant quasars or the majestic spiral galaxies, this diffuse glow is the sound of the entire story being told at once, a permanent testament to the fact that the cosmos has been alive with energy since the first star broke the silence. But light is not the universe's only messenger. There are other, far more elusive signals that travel directly from the heart of cosmic violence, carrying stories that light cannot. The first are neutrinos, the universe's ultimate ghosts. These subatomic particles are so tiny and indifferent that trillions of them pass through your body every second, day and night, without a single interaction. They are produced in staggering numbers in the nuclear furnaces of stars and in cataclysmic events like supernovae. Because they barely interact with matter, they escape from places light cannot penetrate, like the very core of a collapsing star. Detecting them requires extraordinary ingenuity. Experiments like IceCube, a colossal observatory buried deep in the Antarctic ice, uses the frozen continent itself as a detector. When a rare neutrino does interact, it produces a faint flash of blue light in the ice, allowing scientists to trace its origin back to a specific point in the sky. Neutrino astronomy gives us a direct, unedited view into the most energetic and hidden processes in the cosmos. The second new messenger is even more profound: gravitational waves. These are not particles but literal ripples in the fabric of spacetime itself, predicted by Einstein over a century ago. They are generated by the most violent motions of mass, like two black holes spiraling into each other at nearly the speed of light. When such an event occurs, it sends a tremor through the cosmos, stretching and squeezing space itself as the wave passes by. Detecting this minuscule stretching is one of science's greatest achievements. Observatories like LIGO and Virgo use lasers traveling down miles-long vacuum tunnels to measure distortions smaller than 1/10,000th the width of a proton. When they detect a wave, they are listening to the universe ring like a bell. The first direct detection in 2015 was a seismic moment, confirming a major prediction of general relativity and opening an entirely new window on the cosmos. These messengers provide information that is complementary and often revolutionary. Neutrinos tell us about the inner workings of a supernova in real time, while gravitational waves reveal the precise dance of invisible objects like black holes. Most powerful of all is when these signals arrive together with a flash of light. This is multi-messenger astronomy. In 2017, gravitational waves from two colliding neutron stars were detected. Seconds later, telescopes around the world saw a corresponding flash of gamma rays and then a glowing kilonova, an explosion that forged heavy elements like gold and platinum. For the first time, we observed the same cosmic event through sound, touch, and sight, creating a complete, multidimensional picture of a single chapter in cosmic history. These new messengers remind us that the universe's story is not told in a single voice, but in a grand symphony. Light provides the brilliant, detailed imagery. Neutrinos offer the secret internal monologue. Gravitational waves give us the soundtrack, the deep vibrations of spacetime itself. Together, they are writing a richer, more complete biography of the cosmos, one that is still being decoded with every new signal from the dark. This master key, redshift, is the fundamental tool for arranging the entire cosmic story in order. Light does not arrive at our telescopes unchanged after its epic journey. The expansion of space itself, the stretching of the fabric between galaxies, leaves a direct imprint on every photon. As light travels across this growing void, its wavelength is literally stretched along with the space it moves through. Think of drawing a wave on a deflated balloon, then slowly inflating it. The wave itself gets longer, its peaks farther apart. For light, a longer wavelength means a shift toward the red end of the spectrum. This is cosmological redshift, and it is profoundly different from the more familiar Doppler effect. The Doppler shift occurs because an object is moving through space, like a siren changing pitch as it races past you. Cosmological redshift happens because the space through which the light is traveling is itself expanding. For the most distant objects, their redshift is not primarily a measure of their speed through space, but a direct record of how much the universe has stretched since the moment that light was emitted. A high redshift number tells us we are seeing an object not just as it was long ago, but as it was when the cosmos itself was significantly more compact. The light from a galaxy with a redshift of 1 has been traveling for about half the age of the universe, and the space through which it traveled has doubled in size during its journey. A redshift of 10 corresponds to a time when the universe was merely a few 100 million years old, a mere infant. So how do astronomers measure this critical number? The most precise method is spectroscopy. By spreading a galaxy's light into a full rainbow spectrum, scientists look for the familiar barcode pattern of absorption or emission lines from elements like hydrogen or oxygen. They know the exact laboratory wavelengths of these lines. By measuring how far these lines have been shifted toward the red, they can calculate the redshift with exquisite accuracy. For fainter, more distant objects, they often use photometry, measuring the brightness of the object through several different color filters. As light is redshifted, it becomes dimmer and redder in predictable ways. By comparing its brightness in, say, a blue filter versus an infrared filter, astronomers can estimate its redshift, building vast catalogs of cosmic distances. This simple measurement, the redshift, is what transforms a two-dimensional image of the night sky into a three-dimensional map of cosmic history. It allows us to arrange galaxies not just by where they appear on the celestial sphere, but by when they existed. We can stack snapshots from different redshifts, different epochs, and watch the universe grow up. It is the ruler that lets us measure the expansion rate over time, leading to the discovery of dark energy. It is the time stamp on every message the cosmos sends us. Without understanding redshift, the night sky is a flat, confusing tapestry. With it, we have the chronological key to the universe's deepest autobiography, written in stretched and fading light. But light's story is not told only in its brightness or its color. It also carries a hidden sense of direction, a subtle property called polarization. To understand it, picture a light wave not as a simple dot but as a vibrating ripple. This vibration has an orientation, a specific plane in which its electric field oscillates. Normally, the light from the sun or a light bulb is unpolarized, meaning its waves vibrate in all possible orientations at once, a chaotic jumble. Polarization occurs when something forces that light to become more orderly. The most common way is through scattering. When sunlight scatters off the molecules in our atmosphere, it becomes partially polarized, which is why polarized sunglasses can cut glare by blocking light vibrating in one specific direction. In the cosmos, this same principle operates on a grand scale. The ancient light of the cosmic microwave background became polarized in the moments just before it was set free. As the final photons scattered off the last free electrons during the era of recombination, the slight unevenness in the universe's density imprinted a specific, gentle pattern on their orientation. This polarization is incredibly faint, a whisper within a whisper, but it holds two distinct and powerful signatures that cosmologists call E-modes and B-modes. The E-mode pattern is the simpler of the two, a radial or curl-free arrangement that is directly linked to those primordial density fluctuations, the same ones that created the hot and cold spots in the temperature map. It is essentially another, cleaner view of the universe's infant blueprint. The B-mode pattern, however, is the true prize. This is a twisting, curling pattern in the polarization, like the swirl left in a cup of coffee after you stir it. Such a pattern cannot be created by simple density variations alone. It requires a shearing force, a twisting of space-time itself. There are two potential sources for this cosmic curl. One is the weak gravitational lensing we discussed earlier, where the gravity of all the matter that formed later subtly warps the E-mode pattern, converting some of it into a lensing B-mode. The other, more profound source could be primordial gravitational waves, the ripples in space-time generated during the universe's violent inflationary birth. Detecting a primordial B-mode signal would be direct evidence of inflation and a probe into energies 1 trillion times beyond any particle collider. Measuring this signal is a monumental technical challenge. It requires instruments of breathtaking sensitivity, cooled to near absolute zero to detect the faintest microwave whispers. Spacecraft like the Planck satellite mapped the E-modes with exquisite detail, while ground-based telescopes like the BICEP array at the South Pole stare at the cleanest patches of sky, trying to isolate the elusive B-mode curl from the foreground fog of our own galaxy's dust. This polarization data is not just a bonus, it is a decoder ring. By adding the dimension of direction to the ancient light, it breaks degeneracies, meaning it helps untangle confusing signals that look similar in the temperature data alone. For instance, it gives us a much clearer picture of the Epoch of Reionization, that later period when the first stars reionized the cosmos, because that event created its own distinct polarization signature. It refines our inventory of the universe's contents and sharpens our tests of cosmic geometry. In essence, polarization lets us read the cosmic fossil in 3 dimensions instead of 2. Where intensity tells us how hot or cold a patch of the early universe was, polarization tells us about the motions and stresses in that plasma, the shearing forces and sound waves that were actively shaping it. It adds a layer of dynamic history to the static snapshot, revealing not just what the infant universe looked like, but what it was doing in the moments before it sent its first and oldest photograph out into the expanding dark. The ancient Afterglow is more than a static picture, it is an active probe. As the cosmic microwave background travels for billions of years to reach us, it does not always pass through empty space. Sometimes its path cuts directly through a massive galaxy cluster, a city of galaxies held together by gravity and filled with an incredibly hot, thin gas. This encounter leaves a subtle but detectable imprint, a shadow and a shift known together as the Sunyaev-Zeldovich Effects. These are not distortions in the fabric of space-time, but direct interactions between the oldest light and some of the hottest matter in the later universe. To understand the first effect, the thermal Sunyaev-Zeldovich effect, imagine the cosmic microwave background photons as a cool, uniform mist drifting through space. When they pass through a galaxy cluster, they encounter a sea of electrons so hot it can reach hundreds of millions of degrees. These electrons are buzzing with tremendous energy. As the cool, low-energy CMB photons collide with these searing electrons, they get a significant energy boost, like a ping-pong ball being struck by a fast-moving paddle. This interaction, called inverse Compton scattering, kicks the photons to a higher energy, effectively shifting them out of the microwave part of the spectrum and leaving a characteristic distortion. From our point of view, this creates a specific shadow at the cluster's location. At the frequencies where we normally see the CMB most brightly, the cluster appears as a slight dim patch, a tiny hole in the afterglow. At higher frequencies, the same cluster can appear as a bright spot. This unique spectral signature is like a cosmic barcode for hot gas, and it has a revolutionary property. It is almost completely independent of distance. Whether a cluster is relatively nearby or at the edge of the observable universe, the thermal SZ effect creates roughly the same magnitude of distortion on the sky. This makes it a phenomenal tool for finding the most massive clusters across cosmic time, building a census of the universe's largest structures without the usual dimming effects of vast distance. But there is a second, even more subtle fingerprint, the kinetic Sunyaev-Zeldovich effect. This one is not about temperature, but about motion. While the CMB defines a universal rest frame, galaxy clusters are not standing still. They are pulled by gravity, streaming along the filaments of the cosmic web in what astronomers call peculiar velocities. If a cluster is moving directly toward us or away from us relative to this CMB frame, the scattering event imparts a tiny Doppler shift to the photons. This shift is minuscule, a change in temperature of mere millionths of a degree, but it carries priceless information. By measuring this kinetic effect, scientists can, in principle, map the bulk flows of these gigantic structures, tracing how gravity is pulling matter across the cosmos on the largest scales. Together, these two effects turn the primordial afterglow into the ultimate backlight. We are not just looking at the CMB, we are using it as a screen. Any galaxy cluster that passes in front of it casts a distinct shadow, revealing its presence, its internal heat, and even its motion. Surveys like the Atacama Cosmology Telescope and the South Pole Telescope scan the microwave sky, hunting for these SZ shadows to catalog thousands of previously unknown clusters. This allows cosmologists to test theories of structure formation and to weigh these clusters, measuring how much of their mass is in the form of the hot, X-ray emitting gas we can see versus the invisible dark matter that dominates their gravity. The Sunyaev-Zeldovich effects beautifully connect the earliest universe to its mature architecture. They show that the oldest light is not just a relic to be studied in isolation, but an active participant in the cosmic story, a backlight that continues to illuminate the evolving structure of everything. That dense thicket of dark lines in a quasar's spectrum is far more than random noise. It is a cosmic forest, and each tree in it tells a story of a specific cloud of hydrogen gas that once stood between that brilliant beacon and our telescopes. This Lyman-Alpha Forest is the universe's most intricate barcode, and decoding it reveals the detailed architecture of the cosmos in its gaseous form. The principle is elegant. As the quasar's intense ultraviolet light journeys toward us, it passes through countless clouds of neutral hydrogen floating in the vast intergalactic medium. Hydrogen atoms are very particular. They absorb one very specific shade of ultraviolet light. So each time the light encounters a cloud, that specific wavelength gets snatched away, leaving a dark absorption line in the quasar's final spectrum. Because the universe is expanding, light from more distant clouds is stretched more. This means each absorption line is shifted from its original position by an amount that directly tells us the distance to that specific cloud. The result is a stunningly detailed timeline. The lines shifted the farthest toward the red end come from the most distant, earliest clouds, while lines with less shift come from clouds closer to us in both space and time. By reading this barcode from red to blue, we are effectively taking a core sample of the universe along a single, laser straight line, sampling the intergalactic gas from the present day all the way back to when the quasar's light first began its journey. But this forest does more than just map locations. The shape and depth of each absorption line are rich with data. A broad, shallow line suggests the hydrogen cloud is warm and turbulent, its atoms moving rapidly. A narrow, deep line indicates a cloud that is cooler and more serene. By analyzing millions of these lines across many quasar spectra, astronomers can reconstruct the temperature and density of the intergalactic medium throughout cosmic history. They can watch it evolve. In the very early universe, the forest is a dense, dark thicket, indicating that space was filled with a pervasive fog of neutral hydrogen. Then, as we look at quasars from slightly later times, the forest begins to thin in a specific way. The very deepest lines, which correspond to the densest neutral clouds, start to disappear, while a thinner forest of weaker lines remains. This is the direct spectral signature of reionization. The fierce ultraviolet light from the first stars and galaxies is breaking apart the hydrogen atoms, ionizing the fog. The dense neutral clouds are being evaporated first, clearing patches in the forest. This intricate pattern is our most direct map of the cosmic web in its pure gaseous state. Those faint absorption lines are not randomly scattered. They trace the filaments and voids predicted by the gravitational blueprint of the cosmic microwave background. The denser collections of lines reveal where the gas has gathered along invisible filaments of dark matter, the future highways for gas flowing into galaxies. The emptier gaps in the forest correspond to the vast cosmic voids. By studying the statistical clustering of these lines, scientists can measure the small-scale structure of matter, testing how well gravity alone explains the clumping of the universe's ordinary atoms. It confirms that the nearly imperceptible ripples from the primordial afterglow did indeed grow over billions of years into the vast filamentary scaffold that cradles all the luminous structures we see today. The Lyman-Alpha Forest is a continuous narrative written in missing light. It connects the smooth simplicity of the infant cosmos directly to the rich, structured complexity that would make our own existence possible, one ultraviolet shadow at a time. The universe's long silence holds a frequency all its own. To hear it, we must learn to listen not with eyes for starlight, but with vast ears tuned to the quietest hum of the cosmos, a whisper on the radio band emitted by the simplest atom in existence. This is the promise of the 21-centimeter line, a revolutionary signal that could finally illuminate the dark ages directly. The physics behind it is beautifully simple. A solitary atom of neutral hydrogen, the universe's primordial building block, has a proton and an electron, each spinning like a tiny top. When the spins of these two particles flip from being aligned to being opposite, the atom releases a minuscule amount of energy as a photon with a very precise wavelength, 21 centimeters. This is called the hyperfine transition. In today's universe, this event is rare and scattered. But in the epoch before the first stars, when all of space was a vast, cool sea of neutral hydrogen, these tiny flips were happening everywhere. The entire cosmos should have been softly singing in this specific radio tone. That ancient song, however, has been traveling for over 13 billion years. The expansion of the universe has stretched that 21-centimeter wavelength dramatically, from centimeters to meters, shifting it deep into the radio part of the spectrum. Detecting this faint, redshifted echo is one of the greatest challenges in modern cosmology. It requires instruments of staggering scale and sensitivity. Projects like the Square Kilometre Array, or SKA, represent this ambition. When completed, it will be a network of thousands of radio antennas spread across continents, forming a collective ear with a total collecting area of, as the name suggests, a square kilometer. Its goal is not to take a single picture, but to create a three-dimensional tomographic map of the early universe. By tuning its antennas to different radio frequencies, which correspond to different redshifts, it will slice the cosmic timeline. It will listen to the 21-centimeter song as it changes over millions of years, building up a moving picture of the cosmos during its darkest chapter. What would such a map reveal? First, it would show us the gravitational landscape of the early universe in exquisite detail. the subtle density variations from the cosmic microwave background would have begun to gently sculpt the hydrogen gas. The map would show where the gas was slightly denser, tracing the invisible scaffolding of dark matter as it started to pull matter together, long before any star ignited. We would witness the birth of the very first structures, the proto-galactic clumps that were the seeds of everything to come. Then we would see the drama of cosmic dawn unfold in real time. As the first stars and black holes switched on, their fierce ultraviolet and X-ray radiation would have begun to heat the surrounding hydrogen gas and eventually rip the electrons from the atoms once more during reionization. This heating and ionization would leave a clear imprint on the 21-centimeter signal, effectively turning parts of the cosmic radio's song off or distorting its pitch. By mapping where and when these changes occur, we could watch the bubbles of ionization grow and merge, pinpointing the locations of the universe's first luminous objects. This would transform the Dark Ages from a theoretical gap in our knowledge into an observable epoch, a period we can study as directly as we now study galaxies. The 21-centimeter line is more than a signal, it is a direct line to a forgotten age. It uses the most fundamental atom as a probe and the quiet of the radio sky as a canvas. Success would give us a front-row seat to the universe's most formative era, watching the simple, dark cosmos awaken and become complex. It promises to turn the long night between the Afterglow and the first galaxies into a story told in vivid radio light, filling the final blank pages in our cosmic history book with a narrative of gathering gravity and the first faint stirrings of light. The story written in light is meaningless without a scale. To truly read the cosmos as a historical record, we must know not just when an event happened, but how far away it occurred. This requires a meticulous chain of measurement, a celestial ruler built one careful step at a time. We call this the cosmic distance ladder, and its construction is one of astronomy's greatest and most patient achievements. The process begins in our own galactic neighborhood with a method as old as astronomy itself, parallax. Hold your finger in front of your face and close one eye, then switch eyes. Your finger appears to jump against the background. That shift is parallax. For stars, we use the Earth's orbit as our two eyes. By observing a nearby star from opposite sides of our orbit, 6 months apart, we can measure its tiny apparent shift against more distant stars. This geometric method gives us a direct, rock-solid distance to stars within a few thousand light-years. These become our first crucial rung on the ladder. But to reach beyond our galaxy, we need a brighter beacon. This is where Cepheid variable stars become essential. These are pulsating stars whose brightness rises and falls with a very regular period. In the early 1900s, astronomer Henrietta Leavitt discovered a beautiful relationship. The longer a Cepheid's pulsation period, the greater its true, intrinsic luminosity. This period luminosity relation transformed them into what astronomers call standard candles. If you can measure a Cepheid's period, you know its true brightness. By comparing that known brightness to how dim it appears from Earth, you can calculate its distance with remarkable accuracy. Using the nearby Cepheids whose distances were pinned down by parallax, we calibrate the entire class. Then we can find Cepheids in nearby galaxies, measure their periods, and determine the distances to those galaxies. This was how Edwin Hubble first proved that the spiral nebulae were separate island universes far beyond the Milky Way. With the distances to nearby galaxies established, we can search for even brighter, more powerful standard candles within them. The most important of these are Type 1, a supernova. As we discussed, these stellar explosions always occur at nearly the same critical mass, so they reach nearly the same peak brightness. They are so brilliant they can outshine their entire host galaxy, making them visible across billions of light-years. We use the galaxies with known distances from Cepheids to calibrate the exact luminosity of Type 1, a supernova. Once calibrated, these supernovae become our mileposts for the middle reaches of the universe. Each rung of the ladder depends on the one below it. Parallax calibrates Cepheids. Cepheids calibrate nearby galaxies, which calibrate Type 1, a supernova. And supernovae allow us to confidently measure distances to galaxies so far that their light is dominated by cosmological redshift. It is this meticulous, interlocking calibration that allows us to take the redshift of a galaxy's light, a simple measurement of how stretched its spectrum is, and translate it into a precise distance and a specific moment in cosmic history. The ultimate goal of this entire process is to measure the Hubble constant, the current rate of the universe's expansion. It is the number that tells us how fast space is stretching at this very moment. But here lies a fascinating modern tension. Measurements of the Hubble constant using the early universe from the cosmic microwave background give one very precise value. Measurements using the local universe from Cepheids and supernova in the distance ladder give another precise value, and they do not quite agree. This discrepancy is not an error, it is a clue. It suggests something may be missing from our model of cosmic evolution, perhaps a subtle property of dark energy or a new type of neutrino. The cosmic distance ladder is more than a tool, it is a test. Its careful, rung-by-rung construction is what gives us the confidence to claim we know the age and size of the universe, and any persistent wobble in that ladder is not a sign of failure, but an invitation to discover what lies beyond our current understanding. The cosmos holds a profound secret, a hidden architecture that light can only trace by its absence. For every brilliant galaxy we see, there exists a vast, invisible counterpart, a gravitational anchor that does not shine, absorb, or reflect a single photon. This is dark matter, and we know it exists only because of the way it sculpts the light we can observe. The first compelling clue came not from deep space, but from the motion of stars within our own galactic neighborhood. According to the laws of gravity, stars orbiting the center of a spiral galaxy should behave like planets in our solar system. Those closer to the center, feeling a stronger pull, should orbit quickly, while stars farther out in the faint spiral arms should move more slowly. But when astronomers measured these rotation curves, they found something astonishing. The outer stars were moving just as fast as the inner ones, as if gripped by an unseen hand. The visible disk of stars and gas simply did not contain enough mass to explain this motion. The only logical conclusion was that each galaxy is embedded within a massive, diffuse halo of something that exerts gravity but remains completely dark, a halo that extends far beyond the galaxy's luminous edge. This invisible presence reveals itself even more dramatically on the grandest scales through gravitational lensing. When we see the distorted arcs and multiple images of a background galaxy, we are mapping the total mass of the foreground cluster, including its dark matter halo. The distortion is often far greater than the visible galaxies alone can account for, painting a clear picture of an unseen mass distribution that bends the paths of light rays. Furthermore, the pattern of hot and cold spots in the cosmic microwave background, those primordial seeds, could not have evolved into the web of galaxies we see today without the gravitational scaffolding of dark matter. Ordinary matter, the protons and neutrons that make up stars and planets, was too busy interacting with light in the early universe. It was buffeted by radiation pressure, preventing it from clumping efficiently on its own. Dark matter, unaffected by light, could begin collapsing under its own gravity immediately, forming the gravitational wells into which ordinary matter would later flow. The precise measurements of the CMB anisotropy, combined with maps of millions of galaxies from large-scale surveys, tell us this dark component must be cold, meaning its particles moved slowly in the early universe, allowing small structures to form first. They also tell us it makes up about 5 times more of the universe's mass than all the ordinary atoms we are made of. Thus, light acts as our ultimate proxy. We cannot see the dark matter, but we see its shadow everywhere. We see it in the unexpectedly swift dance of stars at a galaxy's edge. We see it in the warped mirages of distant light. We see its necessity written into the very blueprint of the cosmos and the growth of structure across time. Every photon that reaches our telescopes has traveled a path dictated not only by the luminous masses along its journey, but by this vast, unseen landscape. In mapping the light, we are, in essence, drawing the silhouette of the dark. This realization shifts our cosmic perspective entirely. The stars and galaxies we admire are not the main actors, but brilliant tracer particles, illuminating the contours of a hidden reality that shapes the fate of everything. This acceleration is the universe's most startling plot twist. For most of the 20th century, scientists believed the cosmic expansion was slowing down, gradually braked by the collective gravity of all matter pulling everything inward. The grand question was whether that gravity would one day reverse the expansion in a big crunch, or merely slow it toward a distant halt. Then, in the late 1990s, two independent teams made the same shocking observation. By meticulously measuring the apparent brightness of distant Type 1, a supernova, those perfect standard candles, they found these exploding stars were fainter than they should have been. In a universe whose expansion was decelerating, distant supernovae should appear relatively bright because the space between us and them would have stretched more slowly in the past, placing them closer than a simple linear expansion would predict. Instead, they were dim. The only explanation was that these supernovae were farther away than anyone had anticipated. The universe in its past had expanded more slowly than it does today. The expansion is not slowing, it is speeding up. Some repulsive force counteracting gravity is pushing galaxies apart. This mysterious component was named dark energy. The signature of this force is written directly into the history of light. Each faint supernova is a data point, a single measurement of the expansion rate at a specific moment in cosmic history. By collecting many such points across vast distances, astronomers could chart how the expansion rate has changed over billions of years. The story told by this light is clear and consistent. For the first several billion years after the Big Bang, gravity dominated. The expansion steadily decelerated as matter pulled on matter. Then, around 5 billion years ago, the balance of power in the cosmos shifted. The density of matter had diluted enough due to the expansion, while the repulsive effect of dark energy, which seems to be tied to space itself, remained constant or even grew stronger. Dark energy's push overcame gravity's pull, and the universe began to accelerate. This transition is now a fundamental chapter in our cosmic timeline. Crucially, this narrative is confirmed by other, completely independent lines of evidence written in light. The cosmic microwave background provides a snapshot of the universe's geometry and total energy density at 380,000 years old. The pattern of its anisotropies tells us the universe is geometrically flat, which requires a specific total density of matter and energy. When we add up all the ordinary matter and dark matter we can account for through other observations, we come up short. A large additional component is needed to reach that critical density, and its properties must be consistent with something that does not clump like matter but smoothly permeates space. That component is dark energy. Furthermore, the Baryon acoustic oscillations, those frozen sound waves from the early universe, act as a standard ruler at different epochs. By measuring how the apparent size of this ruler changes across cosmic time, we get another independent measurement of the expansion history. This data also points unmistakably to an acceleration that began billions of years ago. Together, these three pillars, supernova, the CMB, and Baryon acoustic oscillations, converge on a single, startling cosmic recipe. Our universe is made of about 5% ordinary matter, the stuff of stars, planets, and us. About 27% is dark matter, the invisible gravitational glue, and a dominant 68% is dark energy, the repulsive force driving the acceleration. This means the universe we see, all the glittering galaxies and nebulae, is merely the visible foam on a dark, energetic ocean whose true nature remains a profound mystery. Light has documented this takeover. Every photon from a distant supernova, every subtle pattern in the ancient afterglow, every statistical preference in galaxy spacing carries the imprint of this transition, the moment the cosmos switched from slowing down to speeding up. We live in an accelerating universe, a fact written not in speculation, but in the faded light of exploded stars and the whisper-thin echo of creation itself. On August 17, 2017, the universe sent us a message in 3 different languages. For the first time in history, we received a coordinated signal, a single cosmic event narrated through gravity, light, and matter. It began with a subtle chirp, a ripple in spacetime lasting about 100 seconds, detected by the LIGO and Virgo gravitational wave observatories. The signal, named GW170817, had the unmistakable fingerprint of 2 neutron stars, the ultra-dense cores of dead stars, spiraling together in a final, fatal dance. Within seconds, space-based gamma-ray telescopes caught a short, powerful burst of high-energy light from the same patch of sky. The gravitational wave signal had provided a rough map, and the gamma-ray burst gave us a precise celestial address. Astronomers around the world swiveled their telescopes, from radio dishes to optical scopes to X-ray observatories, toward a faint galaxy 130 million light-years away. What they witnessed next was a new kind of cosmic firework, a kilonova. This was not the brilliant, star-destroying flash of a supernova, but a longer, cooler glow powered by the radioactive decay of heavy elements freshly forged in the merger's debris. The light from this kilonova was a Rosetta Stone for cosmic chemistry. Its evolving spectrum, shifting from blue to deep red over days, carried the direct signatures of newly created elements like strontium, tellurium, and most poetically, gold and platinum. In that single event, we observed the long-theorized origin story for the heaviest elements in the periodic table, the very material of jewelry and electronics, created in a cataclysm of unimaginable violence. This multi-messenger observation was a transformative moment for science. The gravitational waves told us the nature and masses of the objects involved. The gamma-ray burst confirmed a theoretical link between neutron star mergers and these powerful explosions. The light across all other wavelengths revealed the aftermath, the chemical output, and the environment. Crucially, because we received both a gravitational wave signal, which carries direct distance information, and the light, which identified the host galaxy, we gained an entirely new, independent way to measure the expansion rate of the universe. It was a cross-check written across the cosmos itself. This event marked the dawn of a new chapter in cosmic history, the multi-messenger era. We are no longer passive readers of a story written in faded light. We have become active listeners to a living cosmos that speaks to us through multiple channels simultaneously. Light gives us the detailed picture, the color, and composition. Gravitational waves provide the soundtrack, the deep vibration of massive bodies in motion. Neutrinos, though not detected from this particular event, promise the internal monologue, a direct signal from the hearts of collapsing stars. When these messengers converge, they do not just add information, they multiply understanding. They allow us to test our most fundamental physics in the most extreme laboratories nature can provide. A single event becomes a complete narrative, a coordinated cosmic bulletin where each line of evidence validates and enriches the others. We are now building observatories designed for this symphony, from next-generation gravitational wave detectors in space to neutrino telescopes spanning cubic kilometers of ice and water. The story of the universe is no longer told in a single voice, but in a chorus, and for the first time, we have learned how to hear them all at once. Our cosmic story is poised for its next great chapter, written not by new theories, but by a new generation of eyes. These are the observatories of tomorrow, colossal instruments designed to catch the faintest whispers from the edge of time itself, transforming our map of cosmic history from a sketch into a high-definition film. Each is a specialized time machine, engineered to answer the specific mysteries left unresolved by the light we have already gathered. The James Webb Space Telescope, already rewriting textbooks, is our infrared archaeologist. Because the expansion of the universe stretches the earliest starlight into the infrared part of the spectrum, Webb's powerful mirrors and sensitive instruments are perfectly tuned to see those first, blurry galaxies not as they are today, but as they were when they were truly newborn. It peers through cosmic dust to witness the assembly of the earliest structures and the violent births and deaths of the first stars, bringing the era of cosmic dawn and reionization into sharp focus for the very first time. While Webb looks deeply at tiny patches of sky, the Nancy Grace Roman Space Telescope will take a breathtakingly wide view. Its primary mission is a cosmic census on an unprecedented scale, designed to capture the subtle fingerprints of dark energy. By measuring the shapes and positions of billions of galaxies and discovering thousands of distant supernovae, Roman will map the expansion history of the universe with exquisite precision, helping us understand why that expansion is accelerating and what the mysterious dark energy truly is. On the ground, the Vera C. Rubin Observatory will execute the legacy survey of space and time, scanning the entire southern sky every few nights for a decade. This relentless watch will create a dynamic, living map of the cosmos, catching fleeting events like supernovae in the act, and revealing the subtle gravitational lensing distortions caused by dark matter on a statistical scale never before possible. It will find the rare and the transient, building a moving picture of cosmic change. To listen to the universe's oldest song, we must turn to the radio quiet of remote deserts. The Square Kilometer Array, a vast network of antennas across 2 continents, will be our most sensitive ear ever built. Its goal is to finally detect the faint, redshifted hum of the 21-centimeter line from the neutral hydrogen of the cosmic dark ages. Success would give us a 3-dimensional movie of the universe before the first stars, watching gravity slowly sculpt the primordial gas into the first protogalaxies. Meanwhile, at the cold, high deserts of Chile and the South Pole, a new generation of cosmic microwave background experiments is taking shape. Projects like the Simons Observatory and the ambitious CMBS-4 will deploy arrays of tens of thousands of ultra-sensitive detectors. Their target is polarization, specifically the elusive curling B-mode pattern that could carry the imprint of primordial gravitational waves from inflation. These instruments will measure the ancient afterglow with a precision we can scarcely imagine, testing our fundamental theories of the universe's explosive first moments. Together, this fleet of next-generation observatories represents a collective leap in perception. They will not just see farther, they will see more clearly, in more colors, and with a more patient gaze than ever before. They are built to transform the faint suggestions in our current data into definitive answers, to trace the invisible threads of dark matter and dark energy directly, and to watch the universe wake up from its long, dark silence. The lost history of the cosmos is not lost forever. It is simply waiting for a light sensitive enough and an ear keen enough to finally tell its full story. Light has shown us the universe's story, but it cannot show us everything. There exists a fundamental boundary to our cosmic view, a horizon set not by the power of our telescopes, but by the nature of time and light itself. This is our particle horizon, the ultimate edge of the observable universe. It represents the maximum distance from which any signal, traveling at the speed of light, could possibly have reached us since the moment of the Big Bang. Every galaxy, every quasar, every photon of the cosmic microwave background lies within this sphere. Beyond it, there are regions of the cosmos whose light has simply not had enough time to cross the vast and expanding gulf to reach our instruments. This horizon is not a physical wall in space, it is a frontier in time. We are forever looking out into a past that grows more distant, but never into a present we can share with those far-off realms. Our view is further constrained by a cosmic curtain drawn in the earliest moments. We speak of seeing the afterglow from 380,000 years after the beginning, but we can see nothing from before that. The era of recombination, when the universe became transparent, acts as a final screen. Any light or signal from the earlier, hotter, denser universe was constantly scattered, absorbed, and re-emitted in the brilliant, opaque fog. That earlier history is hidden from direct view, a lost chapter we can only reconstruct through the forensic evidence it left behind in the patterns of the cosmic microwave background and the abundances of the lightest elements. This means the very first moments of cosmic inflation, the possible birth of multiple universes, or the nature of the singularity itself, may be fundamentally inaccessible to direct observation. They lie behind a permanent veil, and our cosmic view is not just limited in the past, but in the future as well. The startling acceleration driven by dark energy is actively shrinking our observable universe over cosmic time. Galaxies beyond a certain critical distance are being carried away by the expansion of space faster than the light they emit can travel toward us. Their light, though emitted, is fighting a losing battle against the stretching of the fabric between us. They are passing beyond our particle horizon, their signals fading into unreachable redshift. In the far future, an astronomer in our local galactic group will look out upon a profoundly empty sky, where all other galaxy clusters have vanished over the cosmic horizon, leaving behind an island universe in an eternal, expanding dark. So what, then, lies beyond our observable bubble? The remarkable uniformity of the cosmic microwave background offers a compelling clue. The temperature is the same in opposite directions of the sky to 1 part in 100,000, even though those regions were never in causal contact according to standard Big Bang theory. They were too far apart for light or any influence to have traveled between them in the time available. This horizon problem is one of the strongest pieces of evidence for cosmic inflation. The theory suggests that these distant regions were indeed in contact in the universe's first fleeting instance, before a period of hyper-rapid expansion blew them apart. If inflation is correct, then the universe beyond our particle horizon is likely a continuation of the same physical laws and structures, stretching out for distances that are truly incomprehensible, perhaps even infinite. Our observable universe, all 100 billion galaxies of it, would be just one bubble in a vast, eternal cosmic foam. This realization grounds our grand exploration in profound humility. Light is the most powerful messenger we have, but it is a messenger with a finite speed and a history of being trapped. It has delivered to us a breathtakingly detailed biography of our cosmic neighborhood, but it cannot deliver a current newspaper from beyond the horizon, nor a photograph from before the dawn. The history we have decoded is the history light was able to bring us. The rest remains in shadow, waiting not for a better telescope, but for a deeper understanding of the cosmos's own hidden rules. The story light tells is not a collection of disconnected chapters, but a single, coherent narrative. We have gathered the evidence from across the cosmos, and when we assemble it, the pieces click together into a breathtakingly consistent picture, a master timeline of existence known as the Lambda-CDM Model. This is our current best account of the universe from its first fraction of a second to the present day, a story where every type of light we have discussed plays a defining role. It begins with a concept we have hinted at: cosmic inflation. In this model, the universe underwent an unimaginably rapid exponential expansion in its first fleeting moments, smoothing it out and stretching quantum fluctuations into the seeds for all future structure. While we have not yet seen the primordial gravitational waves from this event, its necessity is written in the remarkable uniformity of the cosmic microwave background. That ancient afterglow is our first solid data point, the baby picture from 380,000 years after the beginning. Its precise temperature and the pattern of its tiny ripples give us the initial conditions, the density and geometry of the infant cosmos. From that moment, the timeline unfolds with a logical elegance. The slight over-densities revealed in the CMB, those warmer patches, were the starting blocks. As the universe expanded and cooled into the cosmic dark ages, gravity went to work on these seeds. The dark matter, which we infer from galaxy rotations and gravitational lensing, formed an invisible scaffold first. Ordinary matter then flowed into these gravitational wells. This process is confirmed by the large-scale structure we see today, the cosmic web of galaxies and voids mapped by massive surveys. The light from galaxies at different redshifts shows us this growth in action, revealing how small, chaotic protogalaxies merged over time to form the majestic spirals and ellipticals we see nearby. The 21-centimeter line, once detected, will show us this dark, formative era directly. Then came reionization, the cosmic dawn, the fierce ultraviolet light from the first stars and quasars, whose signatures we see in the Lyman-Alpha Forest, and the polarization of the CMB burned away the primordial hydrogen fog. This transition made the universe transparent to most light, allowing the story to be carried freely from then on. The history of stellar life and death is written in the integrated light of galaxies and the brilliant flashes of supernovae. These exploding stars not only seeded the cosmos with heavy elements but, as standard candles, provided the crucial evidence for the universe's accelerating expansion. This acceleration, driven by dark energy, is the final, dominant chapter in our current timeline. The Lambda-CDM model is quantified with stunning precision. The light from different epochs acts as a cross-checking system. The CMB tells us the universe is 13.8 billion years old and geometrically flat. Galaxy surveys and Baryon acoustic oscillations measure how structure formed, confirming the amounts of dark matter and ordinary matter. Supernovae measure the late-time acceleration, quantifying the dark energy component. The astonishing fact is that these measurements, taken from the first light, the Middle Ages of the universe, and its recent history, all agree on the same numbers. They point to a cosmos made of about 5% ordinary atoms, 27% dark matter, and 68% dark energy. This consistency is a monumental triumph of scientific discovery. It means the light from a dying star billions of years ago, the whisper from the cosmic dawn, and the fossilized glow from the universe's infancy are all telling the same story. They constrain the same parameters, fill in the same timeline, and describe the same unfolding reality. We have woven a single history from a tapestry of photons collected across all of time. Yet for all its power, this model is brilliantly incomplete. It names the dominant components of the cosmos, dark matter and dark energy, but does not tell us what they are. It describes inflation without showing us its engine. The unified timeline is not an end, but a foundation, a map of known territories that boldly outlines the vast and mysterious frontiers still waiting beyond the light. That unified timeline is more than a scientific model, it is a mirror. When we look into the depths of cosmic history, we are also looking back at our own origin story, written not in words but in the very atoms that compose us. The calcium in our bones, the iron in our blood, the oxygen we breathe, Every element heavier than hydrogen and helium was forged in the nuclear furnaces of stars that lived and died long before our sun was born. Their cataclysmic deaths, the supernova we now use as cosmic mileposts, scattered these elemental seeds across the galaxy. Over billions of years, this enriched gas coalesced into new stars, planets, and eventually life. We are, in the most literal sense, the universe becoming aware of itself, a collection of ancient stardust now capable of looking up and tracing the journey home. This connection can feel overwhelming. The scale is incomprehensible, a cosmos 13.8 billion years old, containing 2 trillion galaxies, each with billions of stars. In that immensity, a single human life can seem vanishingly small, a fleeting spark in an eternal dark. Yet, the same science that reveals this scale also reveals our profound intimacy with it. We are not separate observers placed on a tiny stage. We are an expression of the cosmos, a natural continuation of its narrative. As the astronomer Carl Sagan famously reflected, we are a way for the cosmos to know itself. That knowledge transforms insignificance into a deep and resonant belonging. Our existence is a direct physical consequence of the universe's long and creative evolution, from the first quantum ripples to the blazing hearts of giant stars. This entire epic, from the first flash of light to the assembly of planets, was necessary for you to be here, listening to this story. And perhaps most astonishing of all is the method of our discovery. We have never visited these distant epochs. We have no physical artifacts from the cosmic dark ages or the first 3 minutes. Instead, we have used pure reason, guided by the fundamental laws of physics, to become cosmic archaeologists. We have learned to read the faint messages carried by photons, the subtle distortions in space-time, the silent shadows in ancient light. From this, we have reconstructed a history of everything, a biography of existence itself. This achievement stands as a testament to human curiosity and ingenuity. It represents a pinnacle of our desire to understand where we came from and what our place might be in the grand scheme. Decoding light to reveal the lost history of the cosmos is not just a technical endeavor. It is one of the greatest intellectual and philosophical adventures our species has ever undertaken. It reshapes our understanding of reality, not by diminishing our role, but by expanding the story of which we are an inseparable part. We are the universe looking back at itself and beginning to understand the epic poem of its own becoming. The cosmic story we have pieced together is brilliantly coherent, yet it is framed by profound unknowns. For every chapter of history written in light, there remains a frontier where the narrative dissolves into mystery, and it is here, at the edge of our understanding, that the next great discoveries await. These are not small gaps but chasms in our cosmic map, and each one points back to the fundamental language of the universe, light itself, as the key to unlocking it. First and foremost are the twin shadows that dominate our modern cosmos, dark matter and dark energy. We know they exist because of how they sculpt the light from galaxies and the expansion history written in supernovae. But what are they? Is dark matter a sea of yet undiscovered particles, or does it require a modification to our laws of gravity on cosmic scales? Does dark energy represent a constant property of empty space, or is it a dynamic field that could change over time, potentially altering the universe's ultimate fate? Every new, deep map of galaxy shapes, every precise measurement of the cosmic microwave background's subtle distortions, is a search for the unique fingerprint these hidden components leave on the light that passes through their invisible domains. Then there is the universe's violent birth. The theory of inflation elegantly explains the smoothness and structure we see, but we still do not know what powered that exponential expansion. The most promising clue would be the detection of primordial gravitational waves. imprinted as a specific curling pattern in the polarization of the ancient afterglow. Finding that faint B-mode signal in the cosmic microwave background would be like hearing the echo of the Big Bang's first shudder, a direct line to physics at energies we can never recreate on Earth. It remains one of the most intense hunts in all of science. We speak of the first stars ending the cosmic dark ages, but we have never seen one. What were these titans truly like? Were they solitary behemoths hundreds of times the mass of our Sun, or did they form in crowded, frenetic clusters? Their light, stretched into the far infrared, holds the answers. The next generation of observatories will scan the deepest fields, not for the familiar shapes of galaxies, but for the unique chemical signatures of these pristine, first-generation furnaces in the spectra of the most distant objects we can find. Even our well-tested model of cosmic evolution, Lambda-CDM, faces intriguing tensions. The most notable is the Hubble constant discrepancy, where measurements of the universe's current expansion rate from nearby sources disagree with predictions based on the early universe's light. This is not likely an error but a clue. It suggests there might be something missing from our recipe, perhaps a new type of neutrino, an unexpected property of dark energy, or even a flaw in our understanding of the very first moments. Resolving this requires ever more precise readings of the cosmic distance ladder and the ancient afterglow, a cross-examination of light from different epochs. And how did the supermassive black holes that power distant quasars grow so immense so quickly? These cosmic engines, with masses billions of times that of our Sun, appear fully formed when the universe was less than 1 billion years old. Did they seed from the direct collapse of enormous gas clouds, or were they built from mergers of smaller black holes at a breakneck pace? The light from those earliest quasars and the gravitational waves from their mergers are the only records of that frantic era of growth. Each of these mysteries represents a missing paragraph, a blank page in the cosmic history book we are compiling. They remind us that the story is far from finished. The light that has guided us this far has not run out of secrets to tell. It is simply waiting for us to build the tools sensitive enough and ask the questions clever enough to listen more closely. The narrative of the cosmos is still being written, and we are here in this fleeting moment to witness the next chapter unfold. The cosmos does not belong only to professional astronomers with access to mountaintop observatories. That ancient light is a public archive, a story waiting for anyone with curiosity and an internet connection to help read. Today, the treasure trove of data from our greatest telescopes is openly shared, transforming cosmic exploration from a distant academic pursuit into a global, collaborative adventure. This movement is known as citizen science, and it has become a vital part of modern discovery. Projects like Galaxy Zoo pioneered this approach. It presented volunteers with stunning images of galaxies from robotic sky surveys and asked a simple question: is this galaxy a spiral or an ellipse? The human brain is exceptionally good at pattern recognition, often outperforming computers at classifying these complex shapes. Hundreds of thousands of people around the world began clicking, sorting, and discussing. What began as a simple classification project led to remarkable serendipity. Volunteers, dubbed citizen scientists, began noticing strange objects that didn't fit the categories, odd green blobs or peculiar disturbances. One participant, a Dutch schoolteacher named Hanny van Arkel, spotted a mysterious, glowing green cloud near a galaxy. This object, now known as Hanny's voorwerp, became the subject of professional studies, revealing a rare quasar light echo that taught us about the violent histories of galaxies. This was a discovery made not in a university, but in a living room. The infrastructure for this public exploration is built on open data archives. Every breathtaking image and spectrum from missions like the Hubble Space Telescope, the planet-hunting Kepler Observatory, and the cosmic microwave background mapping Planck satellite is stored in publicly accessible databases. These are not just pretty pictures for screensavers, they are the raw scientific data available for download by anyone. Amateur astronomers with sophisticated backyard setups use this data to track variable stars or monitor active galactic nuclei. University students can propose virtual observations, analyzing archived files to conduct original research for their theses. High school teachers bring real cosmic data into their classrooms, allowing students to measure the redshifts of galaxies or the light curves of supernovae with the same tools used by professionals. This openness serves a purpose far deeper than convenience. It cultivates a scientifically literate public, demystifying the process of discovery and making it participatory. When you help classify a galaxy, you are not just playing a game, you are contributing directly to the mapping of the cosmic web. When you sift through Kepler data looking for the telltale dip of an exoplanet transit, you are joining the search for other worlds. This engagement is crucial for the long-term health of scientific endeavor. It builds broad support for funding ambitious missions, and more importantly, it inspires. A child who measures the expansion of the universe using real data from a space telescope is not just learning a fact, they are experiencing the thrill of finding something out for themselves. They are connecting to the long human story of looking up and wondering. The light from the cosmos has traveled for eons to reach us, a gift from the depths of time and space. That it now arrives on our personal screens, inviting us all to become explorers, is one of the most beautiful developments in the history of our quest. This democratization of discovery ensures the story of the universe will be read by countless eyes, each bringing a unique perspective and perhaps the next revolutionary insight. These cosmic mysteries demand more than just observation, they require experimentation. Yet we cannot rewind the universe and run it again under different rules. Instead, we have built the next best thing, entire cosmos inside supercomputers. This is the art of simulation, where scientists test the story of light by creating virtual universes from scratch. The process begins with a single, pristine snapshot, the initial conditions taken directly from the cosmic microwave background. Into a virtual box of space, programmers imprint those subtle ripples, the exact pattern of density variations we observe in the ancient Afterglow. They then fill this box with the ingredients of our standard model: dark energy, dark matter, and ordinary atoms, all governed by the laws of physics as we understand them. With a press of a button, they set time in motion. Gravity begins its work. Over billions of simulated years, watched in a matter of weeks, dark matter clumps into a vast, invisible web. Gas flows along these filaments, cooling and collapsing into glowing knots that become virtual galaxies. Stars ignite within them, live, and explode, polluting the gas with heavy elements. Supermassive black holes form at the centers, growing and sometimes erupting with energy. The most ambitious of these projects, like Illustris TNG or the Millennium Simulation, track not just the gravity, but the complex physics of gas hydrodynamics, magnetic fields, and stellar feedback. They are not simple animations, they are rigorous computational experiments that generate a predicted universe, and with that prediction comes a new kind of light. These simulations do not just calculate where mass is, they estimate how it would shine. Algorithms assign virtual stars of different ages and temperatures to the gas particles, and from that they generate synthetic starlight. They calculate how that light would be absorbed and re-emitted by virtual dust. They can even produce mock observations, virtual telescope images and spectra of their simulated galaxies, complete with redshift. This creates a direct apples-to-apples comparison. Scientists can take a survey of the real night sky, with its specific distribution of galaxy shapes, sizes, and colors, and hold it up against the sky generated by the simulation. They can count galaxy clusters at different distances and compare the numbers. They can analyze the virtual Lyman-Alpha Forest or the statistical clustering of galaxies and see if it matches the intricate patterns we observe in the real data. When the simulated light aligns beautifully with the observed light, it is a powerful validation. It suggests our theoretical ingredients, the mix of dark matter and dark energy, and our rules for star formation and feedback are capturing something true about cosmic history. But the true value often lies in the mismatch. When the virtual universe looks too clumpy, or its galaxies are too bright, or its black holes too quiet, it signals missing physics. Perhaps the way supernovae blow gas out of galaxies is more efficient than we thought. Maybe dark matter interacts with itself in subtle ways. These discrepancies are not failures, they are guideposts pointing theorists toward the physical processes they need to understand more deeply. In this way, the simulation becomes a virtual laboratory, a space where we can rerun the cosmos with tweaked parameters. What if gravity behaves differently on vast scales? What if dark energy is not constant but dynamic? By adjusting the rules and watching how the simulated light changes, we can test which versions of reality produce a universe that looks like our own. These digital cosmos are the crucial bridge between the raw story carried by photons and our theoretical understanding of why that story unfolded as it did. They allow us to experiment with history itself, to ask not just what happened, but why it had to happen that way, and what other possibilities were left behind in the darkness. The universe's grand narrative is carried on beams of light, but that light does not always travel through a perfect vacuum. It must pass through a pervasive cosmic fog, a haze of microscopic grains that can dim, redden, and completely obscure the messages we seek to read. This is interstellar and intergalactic dust, and it is one of the most significant obstacles in our quest to see the cosmos clearly. These are not specks of household dirt, but exquisite grains of carbon, graphite, and silicate, smaller than a wavelength of visible light, forged in the cooling atmospheres of aging stars and scattered into space by stellar winds and supernova explosions. They drift through the vast voids between stars and even between galaxies, a fine mist of processed starlight that has been part of the cosmic ecosystem for billions of years. When light from a distant star or galaxy encounters this dust, two things happen. First, the grains absorb and scatter the light, an effect astronomers call extinction. This simply means the object appears dimmer than it truly is, as if viewed through a dirty window. Second, this scattering is not equal for all colors. Shorter wavelengths, the blue and ultraviolet light, are scattered much more efficiently than the longer, red wavelengths. This selective scattering, the same physics that makes our sunsets red, causes a phenomenon known as reddening. The distant object appears not just dimmer, but also redder than it actually is. For a cosmic historian, this is a serious complication. If we are using the color or brightness of a supernova to measure its distance, or the spectrum of a galaxy to determine its age and composition, dust can lead us to profoundly incorrect conclusions. A galaxy might look red because it is old and full of cool stars, or it might look red because its blue light has been stolen by dust. A supernova might appear faint because it is incredibly far away, or because its light is being filtered through a galactic dust lane. To read the true story, we must learn to see through the fog. Astronomers have developed sophisticated methods to correct for these effects. The key is multi-wavelength observation. By looking at the same object not just in visible light, but in infrared and radio waves, we can peer around the dust. Infrared light, with its longer wavelength, passes through dust clouds much more easily than visible light. Radio waves pass through almost unimpeded. By comparing what we see in different parts of the spectrum, we can measure exactly how much reddening and dimming the dust has caused and subtract its effect. We also have detailed maps of dust distribution within our own galaxy from missions like Planck, which measured the dust's own faint microwave emission. These maps act as a correction filter for observations looking out through the plane of the Milky Way. Yet, in a beautiful cosmic irony, this veil is also a storyteller. Dust is not just an obstacle, it is a vital component of the narrative. Those tiny grains represent the processed material from generations of stars, the solid matter that will one day coalesce into new planetary systems. And when dust is heated by nearby starlight, it does not just block light, it glows. It re-radiates the absorbed energy as a warm, infrared glow. This is why infrared telescopes like Spitzer and now the James Webb Space Telescope are so revolutionary. They see the universe not in spite of the dust, but because of it. Where our visible light telescopes see only dark, opaque clouds hiding stellar nurseries, Webb's infrared eyes see those same clouds glowing with the embedded heat of newborn stars. The dust becomes a luminous tracer, highlighting the most active sites of star formation, the very cradles where the next generation of stars and planets are being built. So dust plays a dual role in our cosmic exploration. It is a frustrating veil that complicates our view, forcing us to be clever detectives to recover the true signal. But it is also a chapter in the story itself, the tangible evidence of stellar life cycles, the building block of future worlds, and when viewed in the right light, a brilliant beacon that guides us to the hidden acts of cosmic creation. The search for cosmic history now turns toward a question of profound intimacy. Having learned to read the light from galaxies and the ancient afterglow, we are training the same principles on a new target, the faint glow of distant worlds, hunting for the chemical whispers of life itself. This is the quest for biosignatures, where light becomes not just a historian but a life detector. The method is an elegant extension of everything we have explored. Just as the spectrum of a star reveals its composition, the delicate light that filters through or reflects off an exoplanet's atmosphere carries a detailed chemical report. Future telescopes, like the planned Habitable Worlds Observatory, will be designed with this singular purpose, to capture that faint signal and spread it into a rainbow, searching for the telltale dark lines that speak of a world's breath. The most promising signatures are combinations that suggest a dynamic, living system. A strong presence of molecular oxygen alongside methane, for instance, is a compelling pair. In an atmosphere, these gases react and destroy each other quickly. Finding them together in significant quantities implies something is continuously replenishing them, and on Earth, that something is life. Plants and microbes constantly pump oxygen and methane into our air, maintaining an atmospheric disequilibrium that would be a bright red flag in the light of another world. But scientists are cautious. They must first rule out geological processes like volcanic activity or unique planetary chemistry that could mimic these signs. The true goal is to identify a robust suite of gases, perhaps including water vapor and nitrous oxide, that together paint a picture too complex and too reminiscent of our own biosphere to be explained by geology alone. Beyond these natural biosignatures lies an even more speculative frontier, technosignatures. These would be the spectral fingerprints not of biology, but of technology. An atmosphere polluted with artificial chemicals like chlorofluorocarbons, or an unusual spike in specific wavelengths of light that suggest city lights or massive solar energy collection, would tell a different story, one of intelligence shaping its environment. The light we analyze would carry the narrative of a civilization's industrial age. Detecting any such signature would instantly transform our cosmic story. It would write an entirely new chapter, one where the universe's long narrative of physical evolution gives rise not just to complexity, but to biology and perhaps consciousness. It would answer the ancient question of whether we are alone, not with speculation but with data written in photons. This application beautifully ties the grand to the personal. The same techniques used to weigh galaxy clusters and date the Big Bang, the meticulous science of reading absorption lines and spectral shifts, are now being refined to sniff the air of planets light years away. It demonstrates that our cosmic archaeology is not a detached study of the distant past, but a toolkit with immediate, breathtaking relevance. The quest to understand where we came from has logically extended to the question of who else might be out there. In training our instruments on these distant points of light, we are seeking to complete the most profound chapter in our universal biography, the story of life arising in the cosmos, and in doing so, we may finally find our story reflected in the light of another world. Our journey through the cosmos is a story told in light. Every photon we have gathered, from the faintest microwave whisper to the brilliant flash of a dying star, carries a fragment of a single, unified narrative. It is a history of breathtaking grandeur, a chronicle that stretches from the first flash of the Big Bang to the glittering tapestry of galaxies we see today. We have followed these messengers across time, learning to decode the information they carry about their birth and their epic journeys. The profound realization is this: by meticulously collecting and interpreting this ancient light, we have pieced together a coherent, evidence-based biography of the universe itself. We have watched gravity sculpt the first structures from quantum seeds, witnessed the long dark ages give way to the dawn of stars, and charted the surprising acceleration of cosmic expansion. Along the way, this light has not just answered questions, it has revealed deeper mysteries, confronting us with the invisible realities of dark matter and the enigmatic push of dark energy. This entire epic reminds us that we are far more than passive observers. We are active participants in this unfolding story. The very atoms that form our bodies were forged in those ancient stellar furnaces. Our curiosity to understand the cosmos is the universe, in a sense, awakening to contemplate its own origins and its own fate. The light is still arriving, carrying new chapters. Our telescopes are still listening, and the next great discovery is waiting just beyond the edge of the known. If this voyage through cosmic history illuminated your own curiosity, there are many more space mysteries to explore. Consider subscribing to continue the journey with us, and let us know in the comments which cosmic mystery, from dark energy to the first stars, fascinates you the most.